Well, hi, everybody. I'm very pleased to introduce Lester Mackey. Lester is a principal researcher at Microsoft Research in New England. He's a former colleague of mine, and I would dearly love to get him back into my department. So the first thing I saw that Lester did was a sequence of matrix versions of Hoofding inequalities for the annals of probability. And more recently, he's been working on Stein kernels, and he's been leading a large group on Stein kernels. And one of the most interesting things I've seen there, it's the first Markov chain Monte Carlo diagnostic that can say that your points were good. Most of the other diagnostics will say that your points were bad, and they don't always say that they're bad when the points are bad. But Lester has a positive diagnostic that can tell you when it had worked. One of the things I'd like to remark about Lester is that he's led lots of teams. So he's leading groups here at Stanford. And as a student, he was second place by minutes or seconds in this very large Netflix challenge to rate movies. After that, he took first place in a prize to predict the progression of amyotrophic lateral sclerosis. And very recently, he was the winner of a major climate forecast rodeo for subseasonal climate. So Lester has published in all 4 of the Institute of Mathematical Statistics journals. So applied and regular statistics, applied and regular probability. He was an excellent teacher in our theory classes. So all of these are reasons why we really want to listen to Lester. Also, there was that time that he prevented me from stepping into a road when he saw a car I didn't see. So I'd like to thank him for that. And today, the title of Lester's talk is Probabilistic Inference and Learning the Stein's Method.
Thanks so much, Art. And thank you also to the organizers for having me here. Today, I thought I would spend my time telling you how we can leverage Stein's method, a powerful tool from probability theory, to solve practical problems in probabilistic inference and learning. And along the way, I'll highlight joint work with a small army of amazing collaborators. So the motivation for this line of work comes from large-scale posterior inference. And to explain what I mean by that, I'd like you to consider the standard task of a logistic regression. So you have a data set. Each data point has a feature vector. I'll call that VL. It's a d-dimensional feature vector. You have L data points. And every data point also has a class label, YL and 0 or 1. And in logistic regression, there is a model that relates the feature vectors to the class labels via this unknown parameter vector beta, determining the mean of the binary class label given the feature vector. Now, if we place a prior on beta, this becomes Bayesian logistic regression. And all I want to highlight about this example is that the generative model for your data is very simple to express. But at the same time, even in this case, the posterior distribution over your unknown parameters is complex. The normalization constant is unknown, exact integration under the distribution is intractable. And so we already have some difficulties. And so what do we do in these cases? Well, it's a standard inferential approach is to use Markov chain Monte Carlo, MCMC, to eventually draw samples from your posterior distribution. And the benefit here is that you can approximate these intractable posterior expectations in red with asymptotically exact sample estimates, these averages in blue. Okay, but there's also a problem. And the problem I want to highlight here is that each new MCMC sample point requires iterating over your entire observed data set. And this can be prohibitive when your data set is large. So what can we do? How do we scale MCMC posterior inference to massive data sets? Well, there's this template solution that's been emerging over the past decade. And the idea is that you can approximate MCMC with what we'll call subset posteriors. That is, instead of running your original chain, use an approximate update on each step that only makes use of a subset of your data. Now, the potential benefit of this is that you can sample more quickly. So that's going to reduce your Monte Carlo variance more rapidly. But there's typically also a penalty. This typically introduces some asymptotic bias. Your target distribution is no longer your stationary distribution. But there's a hope that for a fixed amount of sampling time, the reduction in variance will actually outweigh the bias that's introduced. So I think this is a promising path, but it also introduces a number of new challenges. For instance, how do we go about comparing and evaluating the samples produced by these approximate MCMC procedures? And how do we select samplers and their tuning parameters? Most samplers have hyperparameters. How do we pick them? And a bit more generally, how do we quantify this bias variance trade-off explicitly that I've been alluding to? So there are many standard evaluation criteria for MCMC: effective sample size, trace plots, variance diagnostics, but each of these assumes eventual convergence to the target distribution and doesn't account for the asymptotic bias from approximating the algorithm. So in this talk, I'd like to introduce some new quality measures that are suitable for comparing the quality of approximate MCMC samples. And a bit more generally, I'd like to develop a measure that's suitable for comparing the quality of any two samples that are approximating a common target distribution. So this will be our setup for the talk. We're going to work with continuous distributions P with support equal to all of R to the D, but that could be relaxed to any convex set. And P is going to have a density little p. And we'll say little p is known up to normalization, but for most functions of interest, integration under P is intractable. So we're going to approximate integration under P with a sample. We're given sample points x1 through xn. Together, they define a discrete distribution. We'll call that Qn. And we're going to use that to approximate any integral under P with just an average over our sample points in blue. And at this point, I want to highlight that I'm not going to make any particular assumption about the provenance of the xi's. So they could be sampled from a Markov chain Monte Carlo algorithm. They could come from one of these approximate MCMC algorithms, but they could also come, they could also be deterministic, say generated by a quadrature rule. No matter where they came from, we want to assess the quality of them. Okay, so given the sample, we want to quantify how well sample expectations approximate target expectations, how well EQ approximates EP. And we want to do this in a manner that detects when your sample sequence is converging to your target. And we also want to detect when your sample sequence is not converging to your target. And we want to do this all in a way where it's computationally feasible, so you can go off and use these tools when you want to assess your approximate MCMC algorithms. Okay, well, given the nature of the goal, I think it's natural to consider as a quality measure an integral probability metric, or an IPM for short. This is a measure that measures the maximum discrepancy between sample and target expectations over a large class of real-valued test functions. And in fact, when your function class H is sufficiently large, then convergence of your IPM to 0 implies that your sample sequence is converging to P. And that's great. That means we can detect non-convergence, and that's satisfying requirement 2. Okay, but what's the problem with IPMs? Well, we know that integration under P is intractable for most functions of interest, but integration under P features explicitly in the definition of an IPM. And so most IPMs that we're familiar with, like Wasserstein distances, the Dudley metric, can't actually be computed in practice if we don't know how to integrate under P. So what can we do? Well, one idea is that we could only consider functions that are known a priori to be mean 0 under the target distribution. If we could do this, then we get rid of this integration under P, and then we have a quality measure that only depends on sample expectations. That's something we could potentially deal with, potentially compute. So that seems promising, but I think it raises a number of new questions. How do we find test functions that are mean 0 under the target? Once we find them, will the resulting discrepancy measures actually track sample sequence convergence in the way that we want? And then finally, even if we get rid of EP, we still have this infinite dimensional optimization problem over test functions. So how do we actually solve that in practice? So I'll come back to that third question in a bit. But first, I want to show you how ideas from Stein's method can help us to answer the first two questions. So Stein's method is essentially a recipe for controlling convergence and distribution. It was developed by Charles Stein in the 1960s and 1970s for proving central limit theorems. Here's a distillation of that idea that uses as a 3-step recipe. First, we'd like to identify an operator, let's call that T, that generates mean 0 functions under our target distribution P. Okay, so T is going to take as input functions G and is going to output another function. and we want those functions to all be mean zero. So G is going to be its domain. We have an operator T and a set G. They generate mean zero functions. That's great. That's exactly what we're looking for. I'm not going to tell you how to do this quite yet, but first I'm going to show you what we can do with it once we have it. So if we have our operator T and our domain G, together they'll define what we'll call a Stein discrepancy, which is an IPM type measure that has no explicit integration under P because, well, we've gotten rid of it. All the functions are mean zero under P by design. So that's great. This is the sort of metric we'd like to work with. And then what would you do with the Stein discrepancy if you had it? Well, typically in Stein's method, you would lower bound the Stein discrepancy by some reference IPM that you know and trust, like a Wasserstein distance or Dudley metric. And the idea there is that, well, then if your Stein discrepancy goes to zero, you know your reference IPM is also going to zero. And so QN will be converging to P whenever your Stein discrepancy goes to zero. So you can detect non-convergence. Now, typically to do this, this requires some intensive analysis, but it can be performed once in advance for large classes of distributions. And then you can go off and happily use your Stein discrepancy knowing that it works. The third step in Stein's method is typically to upper bound the Stein discrepancy by any means necessary to demonstrate convergence to zero. Now, this is the least interesting step for us because in practice, we're just going to compute the Stein discrepancy. We'll see the value. We know if it's zero or not. But it's still nice to know that if your sample was converging to P, that your Stein discrepancy would go to zero. So I'll give you some results about this too. So the standard use of this recipe is as an analytical tool to prove convergence, to prove central limit theorems and rates in those central limit theorems. But here, in this talk and in this line of work, we'd like to develop the Stein discrepancy into a practical quality measure that we can use to solve inference problems and to assess our Markov chains. So to understand how we could do this, I'm going to give you a very specific instantiation of this otherwise rather abstract recipe. So first, step one, find a Stein operator T. Find an operator that generates mean zero functions under P. To do this, we're going to appeal to this beautiful idea due to Andrew Barbour. And the idea is simply that if you can identify a Markov process that has P as its stationary distribution, then under very mild conditions, the infinitesimal generator of that process generates mean zero functions under P. Now, I've given you the definition of the generator here. We're not going to need that. We're not going to pay much attention to that in the talk. We're only going to focus on a single Markov process and a single generator, which I've written at the bottom. That's the overdamped Langevin diffusion. Here's its SDE, here's its stochastic differential equation, and here's its associated generator. And what we need, and so from this generator, we're going to form a Stein operator. This is what it looks like. I'll call it TP. And the main thing I want to highlight about the Stein operator is that it depends on P only through the gradient of its log density. So that's something that's potentially computable even if P can't be normalized. And for those who are familiar with the Stein's method literature, you could view this as a multivariate generalization of what's called the density method operator for univariate target distributions. Okay, so we're going to make use of this as our Stein operator. We need to pair it with some sort of Stein set. The first set that we'll consider in this talk, I'll call the classical Stein set. You should view it as functions that are bounded, that have bounded derivatives, and that have Lipschitz derivatives. Okay, so if you take functions that are bounded with bounded derivatives and Lipschitz derivatives, it turns out that if you pass these functions through the Stein operator, they're all going to be mean zero. So that's exactly what we'll want. And together, the Stein operator and this classical Stein set will give us what we'll call classical Stein discrepancy. Okay, so we have this classical Stein discrepancy. Now we want to know, does it detect convergence and non-convergence in the way that we'd like? So what does this mean? This means we want the Stein discrepancy to go to zero if and only if your sample sequence QN is actually converging to P. Now, it turns out in the univariate case, this sort of result is actually known for many target distributions. There we know that the Stein discrepancy goes to zero only if the Wasserstein distance also goes to zero. So that's great. That's exactly the sort of result that we want. But multivariate distributions are much less studied in the Stein's method literature. Relatively few targets have been analyzed. A big exception is a multivariate Gaussian because of its fundamental role in central limit theorems. Another example is the Dirichlet distribution, but few other multivariate targets have been analyzed. So to extend the scope of the literature, my collaborators and I established the following result. I'll call it like a Stein discrepancy Wasserstein equivalence. And it says that if that Langevin diffusion that's powering the operator that I mentioned, that Langevin diffusion underlying the operator couples at an integrable rate, and grad log p is Lipschitz, then your Stein discrepancy goes to 0 if and only if your Wasserstein distance goes to 0, L1 Wasserstein distance. So that's perfect. That's exactly the sort of result that we want. What does it mean that Langevin diffusion couples at an integrable rate? Well, this happens for lots of common target distributions. It certainly happens whenever your target is strongly log concave. It covers the case of the Bayesian logistic regression with Gaussian priors that I mentioned at the start of the talk, but it also holds for other non-log concave distributions, for instance, robust students T regression with Gaussian priors, or even Gaussian mixtures. And I also want to highlight that the conditions of this theorem are certainly not necessary for this sort of equivalence, and we're hoping that it will provide a template for bounding the sign discrepancies for other target distributions. Okay, well, it turns out that a variant of this classical Stein discrepancy is also computable. You can compute it using a linear program, by solving a linear program. So I'm going to show you how and what it looks like when you use this in practice. Here first is just a very simple example to highlight a few properties of a Stein discrepancy. Here, our target distribution is going to be a standard Gaussian, and we're going to assess two different chains. One is just sampling IID from the target, P, and the other is sampling IID for something that's not the target. In red, we have sampling IID from the target. And what I'm doing is I'm evaluating the Stein discrepancy as our sample sequence grows. And what you'd hope to see is that as your sample sequence grows, the Stein discrepancy goes to 0. And indeed, that's what we see. It's going to 0 at a 1/√n rate, which is what you would expect for this example. Meanwhile, in teal, I'm sampling from a student's T distribution that's scaled to have the same mean and variance as the target, but is not the target. It's a different distribution. And what you'd hope here is that if you apply your Stein discrepancy to this sequence, it would tell you this is not the target. It would stay bounded away from 0. And that's exactly what you see. At first, your approximation is getting better, but then it stops getting better because you're not actually improving your approximation to the standard Gaussian. Okay, so that's what happens when you examine the values of the Stein discrepancy. But on top of that, you can also recover the function that optimize that infinite dimensional optimization problem. So remember, we're optimizing over a class of test functions. You can actually recover that test function. And here I'm showing you the test function G for different samples and sample sizes. I think a little bit more interpretable than that test function G is what you get when you pass G through the Stein operator. We'll call that H, because that's the function that should have been mean 0 under the target, but is farthest from being mean 0 under your sample. And what can you see from these sorts of examples? Well, if I'm looking at a student's T, we see that the test functions, the worst case test functions, typically have a lot of mass in the tails. And this is because the student's T is oversampling the tails relative to a Gaussian. So this is how the Stein discrepancy detects that this sample is looking pretty non-Gaussian. Okay, here's a slightly more interesting example. Here we're actually going to study a posterior target distribution. So your target P decomposes into a prior pi and a product of likelihood terms, pi of YL given X, YL are your data points. And here we're going to assess a particular approximate MCMC procedure called stochastic gradient Langevin dynamics. Now, for those familiar, you could view it as an approximation to the Metropolis adjusted Langevin algorithm, or even to the unadjusted Langevin algorithm. On every step, you're going to draw a new point by moving in the direction of the gradient of your log density, but actually the gradient of your log density is too expensive. So you're going to approximate that gradient with a stochastic gradient. You're going to sample a set of your data points and use that as an unbiased estimate of your gradient. You're going to take a step in that direction. You're going to add some Gaussian noise. And then usually you'd like to correct this proposal using Metropolis Hastings, but Metropolis Hastings is too expensive. You have to run through your whole data set. So we're just going to throw that away too. And that's the whole update. That's your proposal. That is your Markov chain. Now, in a situation like this, the step size that you use when you're proposing a direction matters a lot. If your step size is too small, then you experience very slow mixing. Take a look at this triptych of plots that I have at the top. I've highlighted the equidensity contours of our target density here. It's a bimodal target. And you see that the black points represent the iterates of our Markov chain. Here, my step size is too small, so I've barely moved from my starting point. So that's pretty bad. Meanwhile, if my step size is too large, then I end up sampling from a very different distribution because I'm making these proposals, but then I'm always accepting them. I'm never correcting them because I've thrown away Metropolis Hastings. So on the right, I'm showing you what happens if your step size is too big. I'm just bouncing all over the place, and this doesn't really look like my target distribution at all. And so what we'd like to do is pick a step size that leads to the best approximation to our target. And you could imagine trying to use a standard MCMC selection criterion for this, like effective sample size. But if you do that, and I've shown the plot here, effective sample size, here bigger is better. Effective sample size says, just pick the biggest epsilon you can. Pick the largest step size you can, because it's really just a measure of autocorrelation. It's a measure of variance, but it's not accounting for the fact that this chain is not converging to your target distribution. It doesn't account for that asymptotic bias. And so from a variance standpoint, this certainly looks like the best sample, and so it picks this one. If instead you use the Stein discrepancy to assess these different samples and to pick out a step size, it would tell you that a very small step size is bad. Here, lower is better. So a very small step size is bad. A very big step size is also bad, and something in between is better. And the thing in between that it picks in this case is this sample here, which I think you can see from this plot that it provides a much better approximation than the other two extremes. Okay, so I've given you one example of a Stein set, the classical Stein set and its adaptation, which I call graph Stein set that I plotted in the last few examples. But now I want to turn to another option that I think is a bit more user-friendly than the classical. To get there, we're going to dig into the theory of reproducing kernels. And this is inspired by the mean zero RKHS work, or mean zero reproducing kernel work of Oates, Girolami, and Chopin. So what is a reproducing kernel? You think of it as a function that has two arguments. It's symmetric in those two arguments, and it's positive semi-definite, meaning that if I have n points and I form the matrix of pairwise kernel evaluations for those points, then that matrix is always a positive semi-definite matrix. And here's perhaps one of the most common examples of a kernel. It's called a squared exponential or Gaussian kernel. It just looks like a Gaussian distribution evaluated at the difference between x and y. That kernel will appear in our talk, and so will what's called the inverse multi-quadrate kernel, which has a similar appearance, but it has polynomial decay instead of exponential decay. Now, what do we want with these kernels? Well, the main thing that we need is a source of test functions. And so what we like about this kernel is that it's going to generate for us a reproducing kernel Hilbert space. And we're going to use that kernel Hilbert space to choose our new test functions. So given a kernel, I can define what we'll call a kernel Stein set. These are multivariate functions, so they're functions with D components. Each component belongs to the RKHS, and the norms in the RKHS are jointly bounded by 1. That's what the set definition says. And why do I care about this particular set? Well, it has this remarkable property that it yields a closed form Stein discrepancy. That is, I can carry out that infinite dimensional optimization problem over test functions in closed form. How does that work? Well, in this case, if I start with a particular kernel K, I can form a derivative kernel, we'll call it the Stein kernel, by multiplying by P, taking some derivatives and dividing by P again. So I get back the Stein kernel, I'll call it K0, and then I just sum up K0 over all pairs of points. So it turns out the value of the Stein discrepancy involves computing this Stein kernel, evaluating it all over all pairs of points, and then summing those together. So this is an n squared operation, potentially expensive, but it's also very parallelizable. So that's nice. And it's in closed form that makes it very easy to use. Okay, so that's great. We can compute the Stein discrepancy, this what we'll call kernel Stein discrepancy, or KSD for short. But does it detect convergence and non-convergence in the way that we'd like? So first, is it the case that Qn converges to P whenever your Stein discrepancy goes to 0? We'll call that detecting non-convergence. Well, it turns out that in pretty broad generality, this is true for univariate distributions. So if your target distribution belongs to the set script P, I'll define that in a second, but it's similar to the P's we were considering before, and your kernel is translation invariant and has a non-vanishing generalized Fourier transform. This covers most of the standard kernels you've worked with that are translation invariant, like Gaussians and returns and inverse multiquadrics. Then your sample sequence is converging to P whenever your Stein discrepancy goes to 0. So that's exactly the sort of result we want. What sorts of targets are we talking about here? Well, this is very similar to what we saw before. If your grad log P is Lipschitz, and you satisfy what I'll call distant strong log concavity. So this means that you have effectively strong log concavity in the tails, but maybe not locally, then you fall into this class. So this again includes the Bayesian logistic regression with Gaussian priors, the student's T regression with Gaussian priors, which is not log concave, but has log concave tails, and also Gaussian mixtures with common covariance. All right, and so this justifies the use of the KST for the univariate case, but I think in most targets of interest, most targets of interest in posterior inference are multivariate. So what can we say there? Well, in the multivariate case, things become much trickier. It turns out that in higher dimensions, KSDs based on common kernels actually fail to detect non-convergence, even for very simple targets like standard multivariate Gaussian targets. Here's a result. It says that as soon as your dimension is 3 or higher, if you use a kernel that decays too quickly, like a Gaussian kernel or a Matern kernel, or even an inverse multi-quadrate kernel with polynomial decay that's too large, then I can give you a target, a standard Gaussian target, for which you cannot control convergence and distribution. So my sample will send your Stein discrepancy to 0, but it won't converge to P. And that's a big problem. That means that you can't really trust your quality measure. And so why is this happening? Turns out this is happening because kernels with very light tails are ignoring excess mass in the tails. And so you can hide mass there. In fact, the sample that you can use to break the Stein discrepancy just sends all of its mass off to infinity. It's not converging to any probability measure. It's in some sense converging to the 0 measure. And so that's a problem. That measure is not tight. And so how can we deal with this? Well, we saw that this happens when your kernel is decaying too quickly. What if it's decaying more slowly? What if you use one of these inverse multi-quadrate or IMQ kernels with slow decay? Well, it turns out that fixes everything. So if you just use slower decay, if you use the beta in this IMQ kernel between -1 and 0, then you have everything you want. If your target belongs to our target function class and you use this kernel, then if your Stein discrepancy goes to 0, you know your sample sequence is converging weakly to P. And the under the hood here, what's going right is that this kernel can detect non-tight sequences and tell you if your sequence is shooting mass off to infinity. Okay, now that's detecting non-convergence. What about detecting convergence? We also want it to be the case that your Stein discrepancy does go to 0 whenever your sample sequence converges to P. And it turns out that happens in pretty broad generality. If you're using any of your favorite kernels that are twice continuously differentiable and bounded, and again, if your grad log P is Lipschitz and square integrable under P, then your Stein discrepancy goes to 0 whenever your sample sequence converges to P in Wasserstein distance. So this covers many of the standard kernels that you'll use. Okay, so let's see this in practice. Let's look at another example of an approximate MCMC procedure that was designed for scalability. This is called stochastic gradient Fisher scoring. It again approximates the Metropolis adjusted Langevin algorithm, but doesn't use a Metropolis Hastings correction. In the initial paper of An et al., they proposed 2 different variants of this algorithm, one that involves an inversion, a matrix inversion on every step, and the other that approximates that inversion with a diagonal matrix to reduce sampling time. And here we're going to target a 51-dimensional target based on discriminating MNIST handwritten digits. And here we're using a Bayesian logistic regression posterior. So let's see what happens. We're essentially trying to decide between these 2 different sampling algorithms, one which is meant to be more scalable and one which presumably is more accurate. And on the left, I'm showing you the IMQ kernel Stein discrepancy values for these 2 different sample sequences. And here lower is better. And what you see is that basically throughout the sample sizes considered, the full version seems to be much better than the diagonal version. So that's what you take away if you're just looking at this IMQ plot. But you might say, well, you just introduced this measure to me. Why should I believe you? So on the right-hand side, I'm showing you a second external validation of the same 2 samples. And to produce this external validation, I've run a long-running ground truth surrogate chain targeting a target distribution P. And I'm using that as a surrogate for P, so I can just evaluate differences in means and covariances across pairwise marginals. So remember, this is a 51-dimensional target. I'm just showing you pairwise marginals here, and I'm displaying on the top the best and worst approximations for pairwise means and covariances. And what can we read off from this? Well, one thing I read off is that for the diagonal version of the algorithm, in the best case, the covariance approximations are very bad. It's not really getting any of them right. This is the best case pairwise marginal. Meanwhile, for the full version of the algorithm, in the worst case, the pairwise covariances are still quite good. So in every single pairwise marginal, the full version is doing a great job, but in every single pairwise marginal, the diagonal version is doing a poor job. So this is something that you'd probably trust if you saw this sort of evaluation, but the benefit of using the KSD over this approach is that this approach requires access to a ground truth chain that you already trust for inference purposes. Whereas with the KSD, you can just operate on your original samples. Okay, so now here's a big question that I haven't answered yet. What if your grad log P is too expensive to evaluate? So remember that our Stein discrepancy, the only dependence on P is through this gradient of the log density. So, okay, we don't have to compute a normalizing constant, but what if it's too expensive? What if we're in this posterior distribution setting where grad log P involves a sum of a large number of terms? I might not want to compute that at every sample point. So what can I do? Well, one option is to use what we call a stochastic Stein discrepancy. That is, you can, much like we do in approximate MCMC, you can replace each grad log P evaluation in your Stein discrepancy with a stochastic gradient based on a random data point batch. This is what I'm showing you in blue. What happens then? Well, it turns out that the resulting stochastic Stein discrepancies inherit the same convergence control properties that I presented to you, the same properties for standard SDs, with probability 1. So you're still going to detect convergence and detect non-convergence with probability 1 if you use this mini batching technique and save a lot of time along the way. So let's see an example of that working in practice. Here I'm showing you the same example from before, but now instead of evaluating just the full SG of S chain, instead of evaluating the SG of S chain using the full IMQ Stein discrepancy, I'm also showing you stochastic Stein discrepancies, which use much less time per iteration. So in red, I'm showing you the KSD evaluation when I actually evaluate every single data point. There are 10,000 data points in this case. In green, I'm showing you when I spend 1/10 of the time, I only evaluate 1,000 data points per grad log P evaluation. And in blue, I'm using only 100. So it takes 1/100th the number of data point likelihood evaluations, but the results I'm getting, the conclusions I get are exactly the same. In this case, the diagonal version is still much worse than the full version. And indeed, by the time I get to a large sample size, the values are almost indistinguishable across the different discrepancies. But in this last case, I'm using, again, 1/100th of the likelihood evaluations. Okay, so far I've been focusing on sample quality comparison, but there are a number of other applications for which these Stein discrepancies can be used effectively. And so next I want to highlight a great application that was proposed by Chiwolkowski et al. And also by Liu et al. In 2016, and that is using Stein discrepancies for goodness of fit testing. So I'm going to use the Stein discrepancy as a test statistic to determine whether or not a sample was drawn from a particular distribution P. And in the paper by Chiwolkowski et al., they use a test based on a default Gaussian kernel. And they notice that this test works well for low dimensions, but experiences considerable loss of power in higher dimensions. And so we thought, well, perhaps this is related to what I showed before about the breakdown of Stein discrepancies based on Gaussian kernels. So we're going to rerun their test using the IMQ kernel and see what happens. So here, the target is a standard Gaussian in D dimensions. The sample is a spiked Gaussian, so it's not coming from the Gaussian distribution. One of the components is spiked with a uniform component. And we're going to compare a KSD-based test using an IMQ kernel to one based on a Gaussian kernel, and we'll compare both with the standard normality test of Baranhaus and Henze. So what do we see? Well, we see that in low dimensions, all of these tests have full power to detect this departure from Gaussianity. But the Gaussian KST test in particular breaks down rather rapidly as the dimension increases. By the time you're in 25 dimensions, it essentially has no power to detect this departure from Gaussianity. And even the Baranhausen-Henze test is starting to struggle at that point. But if you just swap in this IMQ kernel, which we know actually controls convergence in every dimension, we find that you maintain full power throughout the dimension settings of this experiment. So here's another thought. So far, we've been given a sample and we've just been assessing its quality. What if instead we improve its quality? What if we create a better approximation to our target using these same Stein's discrepancy ideas? And this was exactly the idea of black box importance sampling due to Liu and Li. They said, well, instead of just considering an equally weighted sample, let's optimize the weights to best approximate the target with respect to the KST. And they did this with a Gaussian kernel. We're going to show you the same experiment with an IMQ kernel to see what the gains are. So here, very simple example. Again, your target is multivariate Gaussian, standard multivariate Gaussian. I'm measuring how well you're approximating the mean using either an IID sample or one of these black box importance sampling reweighted samples. And I'm showing you this experiment across from 2 to 100 dimensions. And what we see is that if I just use an IID sample, I get a certain level of error. It's exactly what you'd expect from an IID sample. If you use the Gaussian KSD to optimize the weights, you get significant improvements all the way up to dimension d equals 100. And if you use the IMQ kernel instead, which as I was mentioning before, has better behavior in higher dimensions, you get further improvements in quality. Okay, so far we've been taking in samples and assessing them. What about techniques for generating higher quality samples? One popular proposal for this is called Stein variational gradient descent due to Liu and Wang. This uses the same KSD idea to repeatedly update the locations of n sample points in a way that improves approximation to a target. And it's shown that this approximates a gradient step in the KL divergence at every step, and that's where the improvement in quality comes from. Now, the algorithm is not yet fully understood. It does have some asymptotic convergence guarantees, and it's also very simple to implement, making it quite popular. But it's worth saying that the updates also cost n squared time because you're updating each of your n points, and every point update requires n time. You could also imagine speeding this up in cases where grad log p is expensive to evaluate. And you can use these same sorts of stochastic Stein discrepancy ideas in the SVGG context. Recently, my collaborators and I showed that if you swap out grad log p for a stochastic gradient, you can recover the same sorts of guarantees with probability 1, but you can spend then many fewer likelihood evaluations to get to the same quality. And that's what I'm showing you here in these various plots on different data sets, where in blue, I'm running the full algorithm where I run through the entire data set on every round. In red, I'm only using 1/10 of the data in every round. And you can see that this leads in practice to much more rapid convergence in terms of RMSE and log likelihoods. Another option for generating new points is to generate them sequentially. So with SVGD, you generate a whole set of points, say randomly, and then you adjust the positions. Here, we're going to generate a single new point at a time, much like you would do in MCMC, but in a different manner. The idea behind Stein points is that you greedily minimize your KSD by adding in a single point at a time. And it turns out that you can use this to send your kernel sign discrepancy to 0 at a known rate, at a square root log n over n rate. A variant of this algorithm, instead of picking each new point optimally over all of R to the D, just optimizes over the iterates of a Markov chain. So if you have a Markov chain that you believe is good for local search in your density, then in every step, you run that Markov chain for a fixed number of iterations, you select amongst those points, and you add that to your greedy minimization set. And that's called Stein point MCMC. And you can see some of the benefits of doing that here. On the left, here's a sample drawn from MCMC. On the right, here's a sample drawn from Stein point MCMC. And in comparison, the main difference you see is that in MCMC, you tend to get much more random clumping and more random gaps in your density. just based on the random behavior of the MCMC walk. And much of this is eliminated by using the Stein point MCMC algorithm. So I'd also want to spend a good bit of time talking about opportunities for future development. First, opportunity. So I'll go through a few and I'll mention some open questions as we go. First, there are important open questions around improving scalability while maintaining convergence control. So I already mentioned that one source of computational demand in these Stein discrepancies is the need to evaluate grad log p at every sample point. And our initial work says that that subsampling terms from grad log p can lead to good behavior. In particular, you get convergence control with probability 1, but there's still opportunities there to improve that analysis, to understand the finite sample behavior of these algorithms, and to provide stronger guarantees. A second place where expense creeps in is in the production of this kernel matrix. So I mentioned that these kernel Stein discrepancies are closed form, but they also take quadratic time. And so there have been a couple of different efforts to improve this. Most of them are on the practical end, and there's still lots of theoretical questions. One of the first was the finite set Stein discrepancies of Jit-Kridum et al. These replace the kernel matrix with a low rank kernel, and this gives you linear runtime, but now convergence control is unclear. So we'd like to understand, what sort of theoretical guarantees do we have for these finite set Stein discrepancies? A second approach due to Jonathan Huggins and myself is called random feature Stein discrepancies. These provide stochastic low rank kernels and near linear runtime. And we can establish high probability convergence control when the moments of your sample sequence are uniformly bounded. But still, even there, we think there are opportunities for improvement. Can you get rid of any conditions on the sample size, on the sample sequence, and still understand that these randomized Stein discrepancies are providing good quality measures? A second direction is exploring the impact of your Stein operator choice. So I've worked with a single operator throughout this talk. It's this Langevin operator inspired by the generator of a Langevin diffusion, but an infinite number of operators characterize your target distribution P. So a natural question is, how is your discrepancy impacted? And how do we select the best operator in practice? It turns out that the Langevin operator is definitely not the right choice for every target distribution. Here's a result from some of our work. It says that if the gradient of your log density is bounded and you're using a kernel that is C0, then your Stein discrepancy will fail to detect non-convergence. That is, there is some sample sequence that will send your Stein discrepancy to 0, but not converge to P. And that's a problem. That's exactly what we want to avoid with these discrepancy measures, but it will happen if you're dealing with heavy-tailed targets with bounded grad log P. Because of this, some of my collaborators and I have exploring other classes of operators. In particular, we've been looking at diffusion Stein operators, which are motivated by the generators of different diffusions that are approximating your target P. And it seems that this could be one way to solve the problem. In particular, this could be one way of dealing with the heavy-tailed distributions more effectively. Another opportunity comes through post-selection inference. So let's think about other inferential tasks that we can solve. We talked about comparing point sets, goodness of fit testing, improving sample quality, generating fresh samples. But there are a variety of other inferential tasks for which I believe the Stein discrepancy tools could be useful. One example is post-selection inference. There you have constrained targets that are arising when testing significance after variable selection. So you run an algorithm like the randomized lasso, and you want to put confidence intervals around your selected parameters. Typically, this means having to approximate or to integrate under a constrained distribution. And recently, my colleagues and I have been developing some solutions for this setting. So algorithms like SVGD, for example, break down in these constrained settings because they either fall out of the constraint set or get stuck on the boundary. So we've been developing alternative algorithms, which we call Stein variational mirror descent and mirrored SVGD, that are inspired by the mirror descent algorithm and optimization. And these allow us to derive confidence intervals for constrained target distributions. I'd also like to mention non-convex optimization as an application. Here, my colleagues and I have some initial exploration, but I think there's much more to be done. The idea here is that if you have an algorithm, if you're trying to optimize a particular non-convex objective, you like to optimize it globally, one option is actually to think of the problem as approximating its Gibbs distribution. So look at the exponential of the function that so say you're minimizing a function f, look at the exponential of minus f times a temperature parameter, and then try to sample from that target. And the question is, like, well, how do you design a good sampling algorithm? Well, you can use the same tools, the same Stein discrepancy tools, to show which Markov chain Monte Carlo algorithms based on discretizing diffusions lead to high quality approximations to those targets. And then you anneal your temperature, and you can get very fine-grained results about convergence. So here I'm showing you a very simple example. This is a non-convex function that we like to optimize. The optimum is right here at 0. If you use something like gradient descent, after 7,000 iterations, you made very little progress because of the inconvenient curvature of the objective function. If you use the Langevin algorithm to try to sample from the Gibbs distribution in this case, you end up spending time just shooting off in the wrong direction for a while. This is why the purple arrow is going backwards. But if you use these tools from these sign discrepancy tools that I've mentioned to design an appropriate diffusion, then you converge to the optimum in 15 steps. And I think there are many other inferential tasks that are of interest, some of which I've worked on to some degree, some of which I haven't worked on, but others in the space that I've highlighted here have. So besides post-selection inference and non-convex optimization, these tools are being rolled out for parameter estimation, for thinning of Markov chains, and also for the design of control variates. And I think there are many other opportunities. So I'll leave this slide up in hopes that it will stimulate some conversation. So thank you for your time.
Well, thank you, Lester. That was amazing. Lots and lots of interesting results and potentially interesting new directions too for people to look at. Do we have any questions? I think the idea is you put them in the chat, and I think Andreas can. I think the question and answer part is not recorded, so that will happen.
Yeah, I will stop now.